the review for test number 4 is going to be graphing an exponential function, but the exponential function, the absolute value of it is less than 1, which actually flips it across the y-axis. And this is something you can always put in your calculator also. We have y equals 1/6 to the x power. Okay, and it's a multiple choice graphing problem. So again, you can always put that in y equals. So put the 1/6 in parentheses. So open 1/6, close. Then go up in your exponent, and then remember your exponent is where you want to put that x. And then let's graph it. So here's what it looks like. So if you'll notice, this looks similar to A and D. So what you're going to want to do is find a distinguishing point, okay? Or look, you can see where does this cross, look how it crosses through the y-axis. So the difference between A and D is A looks like it comes right up the y-axis. D actually crosses it right there. And those are the only two that have that shape. Okay. Number 2. F of x equals 2 to the x plus 5. So the first thing we're going to talk about is what is the base of this problem? What is the base number? Because when you go to graph this, remember that a lot of the graphing problems, the base is automatically set to E instead of being anything else or having you choose it. So remember, you're going to have to change the base to 2 from that E. So let's see. Now, what is this going to do to that graph? You've got x plus 5 inside your exponent. And remember, inside numbers, move your graph horizontally, left and right. But you're going to go opposite of this sign. So this plus 5 actually means you're going to go to the left 5. So remember, when you go in, you'll tell it that you want to do the exponential tool, and then you just click anywhere on your graph. Okay, and what it'll do is it'll put that exponential graph on the grid right where it's supposed to be, and then you're going to shift it to the left 5. So once you do that, once you tell it to horizontally shift to -5, it'll move the graph in the correct direction. Now, remember, it's also going to have down at the bottom, it's going to ask you what you want your base. It's automatically going to be set to E. So you're actually going to have to delete that and set your base to 2 to make it do the right shape for you. Okay, number 3. You have f of x equals 2 to the x plus 5 minus 2. So, same kind of problem. We're just going to have more than one shift. So let's see, what are we going to start off the graph of? Let's see, it's going to be y equals, then it'll have a blank, to the x power. So you put your base here, right? So you're going to put, that's your base, 2 to the x power, and then you're going to shift it somewhere 5 units. And then another blank, 2 units. So let's see, here's what's shifting at 5 units, and just like the last one, it's plus 5. So I'm going to shift it to the left This right here is an outside number. And remember, outside numbers shift you up and down, and you go with the sign. So that -2 is going to shift you down 2.
Hey, Miss Hanson, just to make sure, so if the number is in like the exponent with the x, it's the opposite of what the sign is?
Yeah. So a
Okay.
plus actually moves it to the left, a minus moves it to the right. Correct. Okay, so after that, we got into some real world applications of these exponential problems, talking about investments. Okay, so let's say, suppose that you had $64,000 is invested at 5.5% interest. And it's compounded quarterly. The first thing you're going to do is find the function for the amount to which the investment grows after T years. So let's see what you're going to do. So it's going to talk about A of T. Now, the first thing that's going to be part of your formula that you're going to use for the rest of this problem is the amount of money that was invested on the front end. So 64,000. And then an open parenthesis, then 1 plus. Now, you're going to create this fraction right here. The top number of the fraction is going to be the interest rate, but in decimal form. So I've got to change this interest rate into a decimal form. So let's see, 5.5% really means, let's change that to 5.5%, because right, 0.5 means a half. Now let's change this to decimal form out of that percentage, which means move this decimal 2 places to the left, and then fill in a 0 in that open spot. So 0.055. Now, the number that is the bottom of the fractions is the number of times per year that the investment is compounded. So let's see, or reinvested. Quarterly tells me it's done 4 times a year. Now, up here, this exponent, we're going to have how many times it's compounded again. And then that's where your T is. The T is going to be the number of years that your money is invested. So here's the formula, except for one thing. This right here, they want you to actually write that out as a full decimal, or just combine all that. So just in your calculator, do 1 plus 0.055 over 4. So you get 1.01375 to the 4t. So that is what your first problem, that's the answer to the first part of the problem when it's asking you for the function. Now, the second part of the problem is going to ask you several different times to change the T to the number of years the money has been invested. So that's what is changing. That's your variable, right? The number of years that your money is invested, which will go right there. Now, let me show you a trick. Put this function in your y equals and just put an x in place of that t. So you have 64,000 open parentheses, 1.01375, close, and then go up into your exponent and put your exponent as 4x, right? Because I don't have a t, I just make it an x. Now, remember what I can now look at what? I can look at my table because my t is actually the x in my calculator, right? So what does this want to know? It wants to know after 0 years, after 2 years, after 5 years, and after 10 years. Well, if these are actually my x's, right? I can go to my table. So second table, oh, I didn't put it in y equals, I just put it in my, oh yeah. So what am I looking for in my x column? I'm looking for the different number of years, right? After 0 years, I'm still at $64,000, right? I just put it in. It hasn't had time to make any money on interest. So it's still 64,000. So then after 2 years, again, you're just looking for the 2. You're now at 71,388. Same thing, after 5 years, so just go down to where your t, which is your x, is 5, 84,100. And after 10 years, 110,513. So you can actually put that in your y equals and then go to your table, because all I need to know is the different amounts when this t is those different numbers that I would have been plugging in, right? If you don't use that method, you're going to have to go into your regular part of your calculator each time, type in that whole thing, changing this t every time to whatever the year is. Okay? All right, number 5. On Melissa's 6th birthday, she gets a $2,000 CD that earns 6% interest compounded semi-annually. If the CD matures on her 15th birthday, how much money will be available? Okay, so let's think about what all the information from that we need. Let's see, we're going to need how much was put in initially, the interest rate, how often it's compounded, and plug that into our formula. So again, let's see, the initial investment was $2,000. The interest rate was 6% interest. And this time it was compounded semi-annually. Semi-annually means twice a year. So, let's see. Our formula will be, the initial investment is $2,000. Then 1 plus, let's see, the top of our fraction is going to be the interest rate, but in decimal form. So 6%. So 6 means move it 2 places to the left. So 0.06 over the compounded annually, which is semi-annually, which means twice. Again, that number, same number again. And then the number of years, right? It's not asking me to come up with the formula. It's asking me how much she's going to have at the end of a certain number of years. So it was invested on her 6th birthday, and it matures on her 15th birthday, which would make it 9 years. So let's see what all of this gives me. I'm going to change this to a decimal. So 2,000. Now, in parentheses, I'm going to have 1 plus 0.06 over 2. Gives me 1.03. Now, my exponent, 2 times 9 gives me 18. So let's see what this gives me. 2,000, open parentheses, 1.03 close. Go up into your exponent, 18th power. Round to the nearest cent. So let's see, cent would be 2 places behind the decimal. If I go one more past that, I see that it's a 6, which means I need to round 86 up to 87. So that gives me $3,404.87. All right, number 6. Now we're into logarithms. Now remember, logarithms are like missing exponents. So this says find the logarithm. It's log base 0.1. So you can do this in your calculator. There's a lot of calculator work on this test. So let's see. Remember, where is log base? If you go to math, and then just go straight down to this A, you'll see that this right here is log base. So hit enter. It'll give you the right spots to put these two numbers. So let's see, my base is 10, so I'll put a 10 down in the base spot. Arrow to the right, 0.1. Enter. And it gives me -1. So that's your answer, right? Now you can just do that in your calculator. Now remember how to go back and forth between exponential expressions or equations and logarithms. This right here should check 10 to the -1 power is 0.1 or 1/10, which would be right? If you raise something to the negative power, that means to flip your base. So I would have 1/10 to the first power, which is just 1/10. And this right here, 1/10 and 0.1 are the same thing, right? 1/10 and 1/10, same thing. So this right here is your logarithm, -1. If you do not have, some older calculators, the TI-83s do not have that log base function in their math portion of their calculator, you can use what's called change of base. They all have that log function. You can do log of whatever this is divided by log of this. That will give you the same thing as that log base function in your calculator if you don't have that in your math button. Okay? Number 9. log base 6 of 6 to the third power. So let's think about this. You could put that in your calculator. Or if you know what this means, what does this mean? 6 to that power should equal that. So 6 to what power equals 6 to the third power? 3, right? 6 to the third equals 6 to the third. So this missing number right here, the logarithm is 3. Right? Number 8. Log base 256 of 4. So again, you can use your log base, or you can do log 4 divided by log of 256, or 256 to what power equals 4. So it looks like I'm taking some kind of root of 256, right? Because I'm going from 256 to 4. So again, I can either do log base in my calculator. So math, down to A, log base, put the numbers in the right spot. So 256 and 4, it's going to give me a decimal, 0.25. It says to type a fraction, so 0.25 is 1/4, right? Math, enter if you're not sure. So 1/4 power. So this right here would be 1/4. All right, number 9, log base 37 of 1. So let's think about this. What power do you raise anything to make the answer be equal to 1? The 0 power, right? So 37 to the 0 power is going to be equal to 1. So 0 power is what that logarithm is. So again, if this is a 1, it doesn't really matter what this is, right? Because to raise anything to get a 1, you're going to need that to be 0. Number 10, 11, 12, and 13 all say convert to a logarithmic equation. So what it's going to do is going to give us an exponential equation and ask us to convert it to a logarithmic equation. So I'm actually going to write them all out to show you that this is the same process for each one. So number 10 is 10 to the third power equals 1,000. Number 11 is e to the fourth power equals m. Oh no, there's only 2. Sorry. After that, we're going the other way. So let's see, converting from exponential to logarithmic. So and I'm going to go to a log. Now remember, here is where your base number goes, right? You say log base. This number right here is where your base goes. What is the base of an exponential equation? This number right here. Right? So that's where your base number goes. So log base 10. Now, these two numbers essentially are just going to switch sides of the equal sign. Right? Because think about this. I'm going to need 10 to the third power to equal 1,000. So you're going to have log base 10 of 1,000 equals 3. So again, log, this number will go in the base spot, and then these two switch sides of the equal sign. So same thing here. So this right here, I can either do log base E, or what's another way to say log base E, ln, and then switch these two sides of the equal sign. So ln of m equals 4, or it should be fine with log base E of m equals 4. Log base E and ln are the same thing. All right, number 13 and 14 are giving us a logarithmic equation and asking us to convert it back to an exponential equation. So let's see, number 12 has log base 5 of 625 equals 4, and log base P of m equals negative z. So again, going from logarithmic to exponential now. So let's see, I need to start off with my base. So my base is 5. 5 to this power, so 5 to the 4th power is equal to that number right there, which is 625. So 5 to the 4th equals 625. Same thing over here. Start off with your base, which is a lowercase p. Raise it to this exponent, which is negative z, equals m, capital M. All right, number 14 is a calculator problem. It says use a calculator to find the natural log, base E. So it says ln of 541.6. So it just wants you to punch that in your calculator. You have an ln button right next to the 4. And then type in 541.6. And then I'm sure it says to round it to 4 decimal places. So let's go 4 spots. 1, 2, 3, 4. After that 5 is a 2, which means I just don't need to round it up. So 6.2945. All right, number 15 says find the logarithm using the change of base formula. So you can either use your log base function in your math button of your calculator, so let's see, I've got log base 7 of 13. So I can either just put that in my calculator or do log 13 divided by log 7. Either one of those are going to give me the same thing. So let's do it each way. So let's go to math, down to log base. Type in the numbers in the right spot. So log base 7 of 13 equals, or if I use my change of base formula, I can do log of 13 over log of 7. So log 13 close divided by log 7 close. So you'll notice it gives you the same answer. So if we're rounding to 4 decimals, after that 1 is a 2, so I don't need to round up the 1. So 1.3 3181. All right, number 16 says express as a sum of logarithms. So remember, when we talked about the different log properties that we used once we got into solving logarithmic equations. So let's see, it says log base 10 of 10 times 100, or excuse me, yeah, 100. And it just wants me to rewrite this as a sum of logarithms. So remember, if you have one log and it's written as a multiplication, you can rewrite that and add those two logs together separately. So this will be the same thing as log base 10 of 10 plus log base 10 of 100. All right, number 17 says express as a product. So remember, we use this a lot when we're solving logarithmic equations. It's the property that you use to bring the exponent or to bring the variable that you're solving for out of the exponent. So let's see, you've got log base m of y to the 6th. So remember what this property tells me. If I have a log, I can rewrite this, especially if this is the variable that I'm solving for in an equation, I would need it to come down out of the exponent. I can rewrite this. Remember, your exponents can come down right there. So you're going to have, this is the same thing as 6 log base m of y. All right, number 18. Log base c of x to the 6th, y to the 3rd z. And it says to write this as a sum or difference of logarithms. So let's see. You don't have a difference unless you have a fraction, right? Something over something. So there's not going to be rewritten as a difference. This is going to be rewritten as a sum. So each one of these is going to become its own logarithm, its own log base c. So let's see. The first one I have is log base c of x to the 6th plus log base c again. What's the next one? Y to the 3rd plus the last one, log base c of z. Now, you can't leave logarithms like this with those exponents, which means what happens to each one of these exponents? They will come down as a product in front of those logarithms. So let's see, the 6 will come down. So I have 6 log base c of x plus 3 log base c of y. And then this one didn't have an exponent, so plus log base c of z. So that's a real pain to type that answer in. So make sure I cannot give you any credit on this test for things that are mistyped in if I do not see your scratch. So I have to see your scratch to be able to see that maybe you put the C up here or something, you know, because in any little misstroke on your keyboard is going to count that wrong. Now, luckily, this next one is even more in-depth and complicated. It's got sums and differences, but it's multiple choice, so you won't have to type the answer all the way in. So it says express log base b of p squared q to the 6th over m to the 5th b to the 8th. So this has all kinds of log properties. So let's see, we're going to all be log base b. The ones in the numerator are going to be sums, so we're going to add. Then you're going to subtract the ones in the denominator because that's the quotient rule. If anything is divided by, you can rewrite it as a difference. So let's see, I've got log base b of p squared plus log base b of q to the 6th. So that took care of my numerator. Now I'm going to have minus the denominator one. So minus log base b of m to the 5th minus log base b of b to the 8th. So now several different things are happening here. The exponents need to come down to be turned into products. And look at this last one. Anytime you have this right here is the same thing, log base b of b, that whole thing turns into whatever this exponent is. Okay? Which means that whole, this is just going to turn into minus 8 at the end right there. So now, bringing down the rest of those exponents. So I'm going to have 2 log base b of p plus, bring the 6 down, 6 log base p, log base b of q minus 5 log base b of m, and then minus 8. Okay? If I didn't see this at the beginning, what if I just went ahead and did the same thing I've done to all these other ones and brought down that 8? So I'd have minus 8 log base b of b. I would still need to recognize that there. This right here, if you have log and your base and this number are the same exact thing, that is 1. Right? That property says if your base and what you're taking the log of are the same thing, this whole thing turns into a 1. So I have minus 8 times 1, which again is just that minus 8. Which looks like B. All right, moving along. Number 20. Simplify the expression. So this is written as a difference. So remember, now I can go backwards from a difference and turn it into a fraction or a quotient. I've got ln of x squared plus 13x plus 30 minus ln of x plus 10. So if I'm going to simplify this, the first thing I'm going to want to see it is as written as one logarithm. Since it is subtracted, I can rewrite this as one logarithm and put the first one over the second one. So let's see, I have ln of x squared plus 13x plus 30 over x plus 10. So now that I see that fraction, I'd say, oh my gosh, I bet this simplifies. If I rewrote this numerator in its factored form, then I could simplify this. So let's see. This numerator in its factored form. So let's see, to get x squared, I would need x and x. Factors of 30 that add to 13 would be a positive 10 and a positive 3. If I put that over that x plus 10 in the in the denominator, my x plus 10s would cancel. And I would be left with that ln of x plus 3. Right, number 21, same kind of problem. Log x squared plus 3x plus 2. Minus log x squared minus 1. So I'm going to do the same thing. I'm going to rewrite this as a single logarithm, putting this one over this one since it's subtraction. So I'm going to have log. I'm going to have x squared plus 3x plus 2 over x squared minus 1. And then I'm going to factor each one of those to see if anything will cancel. So let's see. This numerator, in its factored form, it's a factorable trinomial with an x squared, so it'll be x and x. Factors of 2 that will add to 3 would be plus 2 and plus 1. This denominator, it's also factorable. It's a difference of perfect squares, right? 1 is a perfect square because you can use 1 and 1 to get it. So again, x and x for x squared. To get negative 1, I'll need a positive 1 and a negative 1. The x plus 1's cancel. Which means you are going to be left with log of x plus 2 over x minus 1. All right, going to 22. I'm just going to go through, it's going to take me over the 50 minutes, but I'm just going to go ahead and finish this practice for test 4. So that way I don't leave 5 questions to work on Wednesday. Wednesday we'll be able to just go ahead and start reviewing for the final. That way people can go ahead and if they're ready to take this test earlier in the week, they can. All right, number 22 starts off with, this is when we were solving exponential equations. So let's see, we have 2 to the 8x equals 8. The first method that we used said, if you can write the bases of each side of the equal sign as the same thing, then all you need to do is set up your exponents to be equal to each other, right? Can I rewrite this 8 with a base of 2? Is 8 2 to some power? Yeah, 8 is 2 to the 3rd power, right? So I can rewrite this. 2 to the 8x equals 2 to the 3rd power, right? 8 and 2 to the 3rd power are the same thing. So I can rewrite this to where both of my bases are 2. which just means I need to set up my exponents to be equal to each other and solve them for x. So just divide both sides by 8. So x equals 3/8. All right, number 23. 2 to the x power equals 7. So I cannot rewrite 7 as 2 to a certain power to make my exponents equal. So this is why we have the other method. Remember how you get your x out of your exponent is you're going to log both sides, right? I have to log this left side because that's what's going to bring my x out. If I log the left, I have to log the other side. So let's see, I'm going to log both sides because that will bring my x out of my exponent. So on the left, I will have x log 2 equals log 7. And remember, you're always solving for x, so I just need to get rid of this log 2. So I will just divide both sides by log 2. So x equals, and then that's your calculator work. You've got log of 7. So just in your calculator, log 7, close, divided by log 2, close. Get your decimal, and I'm assuming probably, yes, round to 4 decimal places. So 1, 2, 3, 4. After the 3 is a 5, so round that 3 up to a 4. So 2.8074. Number 24. Solve for t, and t is going to be in the exponent. I've got e to the negative 0.37t. Equals 0.70. So let's see, again, I need to bring that t out. If I'm dealing with an e, instead of logging both sides, I'm going to ln both sides. So when I ln both sides, now I can bring this exponent down in front. So let's see, I've got negative 0.37t times ln e equals ln of 0.70. Now remember, what is ln of e? 1. Because what is ln? It's log base e. Well, log base e of e is 1. So anytime you see ln e, that actually is just a 1 right there. So all I have left on this left-hand side is negative 0.37t. So if I'm solving for t, I just need to divide by negative 0.37. So now t equals, then that's your calculator work. So you've got ln 0.70 close. I go ahead and hit enter and then divide that by negative 0.37. Round your answer to 4 decimals. So 0.96398. Oh. So this right here, that 8 is going to actually round that 9 up to a 10, which actually rounds that 3 up to a 4, right? So this 8 is essentially rounding that 39 up to a 40. So 0.9640. right, 25. All right, 25 is that one problem that we had in this section where we had x's in both of our exponents. We have 12 to the x power equals 4 to the x plus 1. So I am going to log both sides. Logging both sides brings my exponents down. So on the left, I have x log 12 equals, here's where we get complicated. On the right, I've got x plus 1 log 4. So this x goes to this, and so does the 1. So let's rewrite it like this. So this right here, I have x log 4 plus 1 log 4, or just log 4. On the left, I still just have x log 12. Now, what are you solving for here? You're solving for x, right? Well, I see x in this term and this term. You don't want to see what you're solving for on two separate sides of your equal sign. So what I'm going to do now is move this term over here. So I'm just going to subtract it off of this side. So minus x log 4 from both sides. So let's see now. On the left, I have x log 12 minus x log 4. On the right, I've got log 4. So now that I have both of my x terms on the left, since they are both terms, that's a greatest common factor, which means I can pull the x out. So if you pull the x out and put in parentheses what is left, I'll have log 12 minus log 4. Still over here, equals log 4. Now I can get x by itself by dividing both sides, but what's going to isolate that x, which is log 12 minus log 4. Now, this does take some kind of crafty calculator work. So what I would do, because once I solve this right-hand side, I'm done, right? Because that cancels. Here's my x equals. I just need to figure out what all that is. So type in log 4, close. Go ahead and hit enter. Now, you want to divide this by, so answer divided by. I want to tell it to divide by this whole thing. So I'm going to do an open parentheses. Now, after my open parentheses, I'll have log 12. Now, remember, when you have a log, it's going to automatically give you an open there. Make sure you close it after your 12. Minus, again, log, it's going to automatically give you that open parentheses. You'll put your 4 there. So I'm going to close this. Now, remember, I also, right, so I've done this. I've closed the parenthesis here. I need another closed parenthesis to close this open. So close, close at the end of that. And then hit enter. And round it to 4 decimals. 1, 2, 3, 4. So after the 8 is a 5. So the 8 will round up to a 9. So 1.2619. All right, that was number 25. Go on to number 26. Solve for x. It says log base 5. 5x minus 1 equals 3. So there I'm solving a logarithmic. So I'm actually, since I just have a log on one side, I'm going to change this to an exponential equation, right? Because I know if this is a log, then if I change it to an exponential equation, I'll have 5 to the third power is going to be equal to what is right here, which is 5x minus 1. So now look what you have. I'm solving for x. I can rewrite 5 to the third power as 125, right? 5 to the third means 5 times 5 times 5. And then solve it for x. So I'm just going to isolate the x by adding the 1. So let's see, 126 equals 5x, and then divide by 5. So x is just going to be equal to 126 over 5. On the solution sheet, it has this written as a decimal. It should take that. It says, all it says is type an exact answer. That is an exact answer. If you did divide that, what would you get? You would get
25.2.
25.2. All right, number 27. We've got log base 3 of c plus 18 minus log base 3 of c plus 8 equals log base 3 of c. So the first thing I want to do is simplify this left side, right? These are both log base 3's that are subtracted. I can simplify that by rewriting that as one logarithm. Since it's subtracted, I'll put the first one over the second one. So now let's see, I've got log base 3 of c plus 18 over c plus 8 equals log base 3 of c. So this one's different than the last one because I have logs on both sides. But remember, I can do anything to one side as long as I do it to the other. So why not just divide both sides by log base 3? Won't that'll just get rid of the logs altogether. So if I divide both sides by log base 3, that's gone, and that's gone. So now let's see what I have. I've got c plus 18 over c plus 8 equals c. So if I'm solving for c here, if your c is in a denominator somewhere, you need to fix that. So here, how do I fix it? That's going to cancel this. If I do it to the left side, I have to do it to the right. So multiplying both sides by c plus 8. So on the left, I've got c plus 18 equals, on the right, I've got c squared plus 8c. So now, what do you notice? You are solving a quadratic equation that you could use your quad program for in your calculator, but before you do that, you've got to get all your terms together on the c squared side, which means I need to subtract c and subtract 18 from both sides. So on the left, I've got 0. On the right, I've got c squared. 8c minus 1c is positive 7c minus 18. Again, you can take that straight to your quad program if you would like, or just factor it. Let's see, it is a factorable trinomial, so c and c. Factors of negative 18 give me positive 7 or a positive 9 and a negative 2. So if I set these equal to 0 and solve them for c, so let's see, I have to subtract 9s here, which would actually give me c equals negative 9. Add 2s here to get c equals 2. Now remember, the c that we're solving for is a logarithm, which means that number right there can't be negative, which means you do not count your negative 9 answer. 2 is the only real answer. All right, 28. All right, another logarithmic equation. So let's see, I've got log base 2 of x plus 2. This one's plus log base 2 of x minus 2 equals 5. So on this one, I am going to simplify the left-hand side using that property of logarithms that says if you have two logs with the same base added together, you can rewrite them as one logarithm with the x plus 2, x minus 2 multiplied. So I've just rewritten this log base 2 as one log base 2 with these multiplied still equals 5. So it's not like the last one. It's actually like the first log equation that we solved because I just have a log on one side. You have a log on one side, change it to an exponential equation, which means 2 to the 5th power is going to be equal to all of that, which is x plus 2, x minus 2. So let's see, 2 to the 5th power means 2 times 2 times 2 times 2 times 2, which is 32, equals, I'm going to have to FOIL this, right? X plus 2, x minus 2. So let's see what that's going to give me. X times x gives me x squared. X times negative 2 is negative 2x. My inner is positive 2x. And my last, positive 2 times negative 2 is negative 4. All right, let's see. This will clean up a little bit because your negative 2x and your positive 2x will cancel. So let's see, I've got x squared minus 4. But once again, it is an x squared equation, which means I need to set it equal to 0 and either put it in my quad program or factor it. So let's see, I need to subtract 32. So let's see, what do I have? On the left side, I've got 0 equals x squared minus 36 so if I factor that, that's an easy factoring problem, right? It's a difference of perfect squares. So x and x for x squared, plus 6 and minus 6 for that negative 36. When you set those equal to 0 and solve them, this will turn into negative 6. This will turn into positive 6. But remember, you're finding the log, which means that cannot be negative, so don't use your negative answer, just your positive answer. All right, 29 says, suppose that 17,073 is invested at an interest rate of 5.7 per year, compounded continuously. So this is a little different than the other ones that I've used, that I did earlier. Compounded continuously means you're going to use an E. That's when the E comes into play. Okay? On the right side of the equal sign is your initial investment. 17,073. Now, instead of what we were doing earlier, which was the 1 plus the interest rate over the number of times it's compounded a year, when you're compounded continuously, you just change that to an E. Now, up here, you're going to have the rate times the number of years. So let's see, it does tell us the rate is 5.7% per year. So I need to change that to a decimal, which makes it 0.057 T. Now, that's your formula that you're going to use. This one says to round it to 2 decimal places. Now, remember earlier we put that in my y equals and then just put in and change the number, looked for the x for the number of years. But my calculator is not set up to round to 2 decimal places like this problem says. So I'm actually going to work out a couple of these and then let you go with the rest. So let's see, the balance after 1 year. So T is the number of years. So after 1 year means just replace that T with a 1. So I'm going to have 17,073 E to the 0.057 times 1. And then just put that in your calculator. So 17,073. And then remember, E to the X is right above the ln. So second ln, to get that E, it automatically puts you up into your exponent. My exponent is 0.057 times 1. So just 0.057. Enter. So after 1 year, rounded to the nearest cent, would be 18,074 and 43 cents. All right, I'm going to skip the next couple, and then it's because then it says 2 years, 5 years, 10 years. So all you're doing is changing this number right here. So I'm going to jump to the end and make that 10. So let's see, you can type it in just like that. So 17,073. Second ln to get your E. Then up in your exponent, 0.057, you can type it in just like it's written. Open parentheses, 10, close, enter. So after 10 years, rounded to the nearest cent, would be 30,189.62. Now, the last part of this problem says the doubling time is blank years. To find the doubling time, you're just going to do ln of 2 over your interest rate written as a decimal. So 0.057, which is going to tell you how fast your money is going to double at this interest rate compounded continuously. So ln of 2 close divided by 0.057. So 12 point, oh, how does it want me to do it? Round to 1 decimal place. So 1 decimal place would be 12.2. All right, last problem. So this one is going to give us, this is the one about the married couples, the percentage of married couples that are declining. So the first thing it's going to do is give us a chart and ask us to find the K, which is the rate at which it is declining. So let's see. The chart starts in 1960. And in 1960, 68.2% of adults are married. And it goes all the way to 2012. And there it says 41.1% of adults are married. So what it wants us to do is find the value of K. K is going to be the percent at which this is declining. So let's see, what you want to do is to set up, my K is going to be in my exponent. So on the left side of your equal sign is the ending number or the final result of percent of adults who are married. So what's the ending percent? 41.4. Is equal
41.1.
Did I do it wrong? Oh, thank you. 41.1.
I was like, hold up, ma'am.
I don't want to mess up at this point. Okay, on the right side of the equal is the beginning number, the initial number. So 68.2. E. Now let's see, this up here is going to give me, my exponent needs to be negative because it's declining, right? So let's see, my KT, I don't know what K is. T is the number of years. How long did it take me to get from 68.2 to 41.1? Well, it took me from 1960 to 2012. Hang on. Okay, so again, here's the chart. So in 1960, 68.2% of adults are married. 2012, 41.1% of adults are married. And it wants me to find the rate at which this is declining, which means my exponent, since I'm declining, I'm going to have a negative. I'm going down. So I'm going to have a negative in my exponent. On the left side of the equal sign is going to be my end number, the end amount, which would be 41.1. On the right side was my initial amount, so 68.2. since it's declining, I'm using that decline, that logarithmic model. So I'm going to have E, it's declining continuously to the, since I'm going down, that's where my negative comes in. The formula is going to have a negative right there. I do not know the rate. The rate is written in as a K. That's what I'm going to solve for. Times T, and T is the number of years it took me to get from 68.2% to 41.1%. So you'll just go back to this chart. From 1960 to 2012 is 52 years. So now let's see what we have. We're solving for K. So the first thing I'm going to do is get rid of this 68.2. So I will divide both sides by 68.2. Get rid of that. So now I have E. Let's see, negative K times 52. This gives me negative 52K equals 41.1 over 68.2. Now, to get the K out of the exponent, or to bring that whole exponent down, I'm going to log both sides, which actually means I'm going to ln, since it's an E. So now, let's see, I've got ln of 41.1 over 68.2 equals, let's bring the exponent down now. So now I have negative 52K ln E. Now remember, what is ln of E? It is equal to 1, since that's log base E of E. So now I just need to get K by itself, which means I need to divide both sides by negative 52. So let's see what that gives me for K. So let's see, I've got ln of 41.1 over 68.2 close, enter. Now I'm going to divide that by that negative 52. So divided by negative 52. So here is the K. 0.0097. That is the rate at which it is declining. So that is the number that you are going to put in for the K from now on. That is the rate. So let's see, M of T. Let's see the function that I can use. For the rest of the problems here, I just need that number right there. So if you are using the decline model, you're going to have M of T equals your original amount. What is the initial original amount? 68.2. E. Now, your formula, since you are declining, is going to have a negative in it this time. That's what's going to tell you to decline. The negative, then KT. Well, now I know what K is, 0.0097 T. So that's going to be your formula. Now, the B part says, estimate the percent of adults who are married in 2015 and 2018. Well, 2015 just means what do I need to put in as my number of years? I know how many years it takes me to get from 1960 to 2015. It takes me 55 years, which means I need to put a 55 in place of that T now. So I'm going to have 68.2 E to the negative 0.0097 calculator. So let's see. I've got 68.2 E. So second ln. Up in my exponent, I have negative 0.0097. And then just like it's written, open parenthesis 55, close it. Enter. So let's see, what percentage is going to be married in 2015, rounded to 1 decimal place? So it looks like 40.0, or just 40. Now, the second part of that is going to say in 2018, which just means you're just going to change this 55 to a 58 and do the same thing you just did for the 55. Now, the very last part of this test is going to say, at this decay rate, in which year will the percent of adults who are married be 34%? So let's see, if I work that out, when will it be 34% in this chart? What year will that be? So what I need to do, 34 is my end number, right? So that's what goes on the left side of your equal sign. So 34 is my end result. My beginning number is 68.2. E to the negative, let's see, 0.0097 T. T is what I don't know. I don't know how many years it's going to take me to get to 34%. So that's what you're trying to find, is how many years it's going to take you. So solving for that T, I need to first divide by 68.2. Get rid of that. So now I've got 34 over 68.2 equals E to the negative 0.0097 T. So if I'm solving for T, I need to get that out of the exponent, which means I need to do what? ln both sides. So that will bring me out of the exponent. So now I have negative 0.0097 T of ln E, which means, remember, that's a 1, equals ln of 34 over 68.2. So in order to solve for this T, I just need to divide both sides by negative 0.0097. That will get my T by itself. So in my calculator, ln of 34 over 68.2, close, enter, divide that by negative 0.0097, round to the nearest whole number. So 71.7 will round to 72. Now, that's what T equals. What the question is asking me is, what year will the rate be 34? Well, it's not the year 72. It's just going to take me 72 years from 1960 to get there. So let's see, 1960 plus 72 gives me 2032.
I'm not gonna lie, Ms. Hanson, I kind of did that like the longer way. Like I started with the equation.
All right, I'm going to say that again since I just stopped recording. So again, I know this one is forever long, but this makes your review for test 4 all on one video instead of split up into 2. So on Wednesday, we'll be able to start reviewing for the final. So I will see y'all Wednesday.
Have a good day, Ms. Hanson.
Thank you. You too.